noche de Vallecas. Y ahora
Good afternoon to all of the people present in this Thursday NanoSpin-off talks and welcome. I am Maria Sancho, researcher from the University of Zaragoza, and today we have the pleasure to have here Daniel Ramos. Daniel Ramos is the principal researcher of the Optomechanics Lab Group at the Material Science Institute of Madrid. He is also coordinator of the quantum sensor line at PTI Plus Quantum Technologies of CSIC, expert member of the technical committee of the ICTS Micro Nanofabrication Clean Room Network, and founder of Nanological, a spin-off company that he is going to talk today. He completed his doctorate in Bio-Nanomechanics Group of CSIC in the University Complutense of Madrid, laying the foundations of biological sensing through the dynamic characterization of nanoresonators. In 2009, he joined the Yale Nano Device Group in United States, doing theoretical and experimental studies related to the stability in dynamic systems driven by optical forces. In 2011, he was awarded with a Marie Curie Fellowship to carry out the OptoNanomech project at Harvard University, whose main goal was the transfer of optical energy confined within energy nanophotonics cavities into the mechanical modes of names. The researcher, Daniel, joined the Harvard Quantum Optics Center and the Harvard Center of Nanoscale Systems, and he then was able to come back to Spain with a Juan de la Cierva scholarship, followed then by a Ramón y Cajal contract, and a distinguished researcher's position with an I3 Certificate of Excellence at the Institute of Micro and Nanotechnology of CSIC. Since December 2021, he is a senior scientist at the Material Science Institute of Madrid. Now, let me present a little bit Nanological, that is the spin-off company that he is going to present. And I know he will talk more about it, but just 2 lines. Nanotechnological is a deep-tech startup developing an innovative in vitro diagnostic platform for the rapid identification of bacterial pathogens directly from blood samples. Originating as a spin-off from the Spanish National Center Council from CSIC, Nanological builds on over a decade of research in advanced optomechanical sensing. Its proprietary technology combines label-free multiparametric detection with artificial intelligence to analyze individual bacteria without the need for prior blood culture. So thank you, Daniel, and welcome to this Thursday Nano Spin-off Talks. And it's going to be a pleasure hearing your talk.
Okay, so thank you very much. Let me try to share my screen to start the presentation. Okay, so thank you very much. It's a real pleasure for me to present the work that we are doing at Nanological for the ultra-fast identification of bacteria for sepsis diagnosis. Let me start just a little bit about myself. I did my PhD at the CSIC, at the Spanish Research Council, doing nanomechanical sensing, mostly for to develop biosensors. Okay, these biosensors were based on the measurement of nanomechanical systems, which are more or less just no more than a spring, basically, right? I used optical forces and optical detection systems for these nanomechanical systems. And that's why I made a postdoc at the United States working on photonics, integrated photonics at the first, and then optomechanical systems. These optomechanical systems combine nanomechanical resonators with optical cavities. Okay, in such a way we can make a regenerative displacement or regenerative oscillation of these nanomechanical sensors to obtain or to improve the signal-to-noise ratio. Just a second. No. Dejo de compartir. Un segundo. Yo aquí tengo mi presentación y ahí se ve así. ¿Vale? Y si yo comparto en Zoom, porque antes se veía bien, ¿verdad? Ah, ya sé lo que pasa. Yo creo que sí comparto. A ver. Ahora sí.
¿Y ahora?
No. Vale, voy a hacer una cosa. Voy a compartir la pantalla. Toda la pantalla. So in this optomechanical sensing scheme, what we do is to use optical cavities in order to make a regenerative oscillation of the nanomechanical sensors in order to improve the noise, basically. Then I got a thinner position at the RFSIC, and that's when I started to develop this technology, which was transferred to Nanological. And right now, I'm the principal investigator of my group at the Material Science Institute of Madrid. Then I would like also to introduce Blanca Caballero, who is the CEO of Nanological. She made her PhD also in photonic sensing, also at the CSIC, doing research on plasmonics and optical sensing. Then she did a data analytic master at the MIT in data analytics and also big data techniques. And then she moved to the industry, to the private companies, mostly dedicated to consultancy firms like KPMG, Deloitte, etc. And she then moved to Repsol in management of product team products, and she's the CEO of Nanological since the incorporation of the company 2021. This is more or less the nanological journey from the basic research that we have been working on since more or less 8 to 10 years, something like that, in which we have different papers, PhD, thesis, patents, etc. In 2020, I made 2 accelerator programs for the company. I participated in Health Start and Dynamiza programs. Then we incorporated Nanological in 2021. However, the licensing of the patents were in 2022. Okay, we didn't start the properly work doing in Nanological more or less one year later, in which we get our first financial round, a Neotech project, NISA, and also private funding. Okay, so this is more or less what the nanological journey till now. So let's be focused on the research part. Okay, what we tried at the beginning was to identify particle in liquids environments, and this is very important. Why? It's because the areas of interest are the environmental studies, for example, microplastic in liquids, etc., pharmaceutics, chemical industry, and also biology and medicine. How can we do that, or how I did that? Okay, I use nanomechanical sensing, basically, which is my main research focus at those years. And here we have a problem, because if we have a nanomechanical resonator oscillating in vacuum, we have very nice peaks, very nice resonance peaks. We have a very high quality factor, etc. However, if we immerse these resonators in liquids, this resonance drops. Also, the quality factor is ruined, and the performance is terrible. So they basically cannot be used for liquids environments. what people do, or what people did at that time, more or less 15 years ago, they proposed a solution, which is the use of hollow nanomechanical resonator, in which the liquid goes inside the resonator and not outside. Therefore, we can make these resonators oscillate in low viscous damping environments, for example, gas or air or even vacuum. And we can apply this for biology and medicine. How does it works, or how people do this single cell detection in liquids? So nowadays, I think that flow cytometry is the most used technique. It's widespread. It's also commercial, but they have it has some drawbacks because they need fluorescence markers, which is costly, and also it cannot allow you to make a very quick analysis from the blood directly, but it has a very high throughput. Okay, so they can be used for cell discerning, and that's what people do usually in clinical research. And we have the hollow nanomechanical resonators. These hollow nanomechanical resonators, as I told you, they have like a suspended microchannel right here, and it's moving. Okay, it's a kind of emerging technique, and it allows to measure different biophysical properties like mass, volume, stiffness, density, etc. Okay, and there are different ways to do these oscillators. For example, we have a cantilever here, but we can also have microchannels or even hollow capillaries. The mechanical or the physical principle behind this is to use those resonators as MEMS. MEMS is a microelectron nanomechanical system, which is basically an oscillator, okay, that can be read out by using electrical, optical, or magnetic fields. In our case, we use optical fields to make the readout. And we have this resonator oscillating here. Okay, if you remember something from your school, you will probably remember that a resonator follows the Hooke's law, which is basically a spring, a mass with a spring. So the frequency of this resonator depends on two different parameters, which is the spring constant, or the stiffness, and the mass of the resonator. Okay, so the spring constant goes in the denominator, and the mass is inversely proportional. So if we put a mass on top of this resonator, this resonance frequency goes down. This is what we call mass effect. Okay, so we can make measurements on the resonance frequency of this resonator to make a measurement of the mass, or the added mass on these sensors. However, as I told you, we have also the stiffness, or the spring constant of these resonators. Whenever we put something on top of a resonator, the stiffness of the system increases. This is what we call the stiffness effect, and the resonance frequency goes up a little bit. Okay, so just with a spring, we can make measurements on the mass and stiffness of whatever we want to sense on top of these nanomechanical or these optomechanical sensors. But we also have microfluidics. Microfluidics allows different things. For example, we can measure hydrodynamic forces acting on particles or cells. We can also deliver some cells very easily just by controlling the pressure on these channels here. Okay, so for this project, we have two different things. We have a nanomechanical resonator, which is very sensitive to the mass and also the stiffness. We have microchannels, which allows the easy particle delivery, and it allows also to measure hydrodynamical forces. And we combine them to use them as suspended microchannel resonators, in which we have something flow inside the channel we want to sense, basically. Okay, So these suspended microchannel resonators provide high throughput. So that means that we can measure a lot of things very easily, very fast. And they have a very, very good sensitivity. In this case, it's 10 attograms. So what else can we do? Can we measure more parameters? Let's think about that. Okay, our approach is to use transparent microcapillary resonators, which we have a suspended microchannel, which is based on silica capillary tube. These silica capillary tube are no more than fiber optics cables, hollow fibers that we change the shape just by using thermal stretching. We hit this part here and we stretch it. We introduce a force, a lateral force, in order to decrease the size here until the desired value, the desired diameter. And then we suspend it by using photolithography. It is a clean room technique. It's a clean room based technique. Okay, so let's see what kind of parameters can we measure with these hollow capillary sensors. We can make measurements on mass, reflectivity, size, compressibility, maybe others. Okay, let's start with the mass. I told you that nanomechanical resonators, in this case, these hollow nanomechanical resonators can make measurements on mass, but it's not entirely true. We can measure is the buoyant mass. This buoyant mass is the difference in between the mass of the particle inside the liquid and the mass of the displaced volume in the liquid. Okay, so whenever a particle goes inside the microchannel, the resonance frequency decreases because of the mass, and then it recovers when goes out. But this is the buoyant mass. Okay, so the buoyant mass is basically the volume of the particle multiplied by the difference in density of the particle and the fluid. Okay, and what happens if we have a mixture of different particles on these liquids? Okay, so let's see here, in which we have silica particles. In this case, were 8 microns and 6 microns particles, and we can distinguish. So there are a lot of different measurements of the buoyant mass. We can distinguish two maxima, depending on this particle size, on these masses. However, if we have a mixture of different particles made by different materials, different sizes, in this case, we have PMMA and silica, 12 microns and 8 microns, which are very different, in between them, the distribution cannot be resolved. We cannot distinguish them, basically, because of the density contrast. What people did at the beginning were to use these hollow nanomechanical resonators, making measurements at different carrier liquids. So they changed basically the liquid. They changed the liquid and they measured several times with different liquids in order to try to discern in between the mass and the density mass of the particle and the liquid. But this technique is very costly. It's also very slow. And since we have transparent resonators made basically by fused silica or by glass, we can have optical access to the system, to the particles flowing inside. These optical access were performed by using an interferometric readout. In this case, what we have is a laser. This laser is focused on the nanomechanical resonator. It reflects on a substrate, and the reflection is collected by a photodetector. And here, the key parameter is how do we treat this signal at the photodetector. We use a locking amplifier to analyze two different components of the signal, the AC component and the DC component. The AC component is modulated at the resonance frequency of the microchannel because of the caused by the displacement of the resonator. And the DC component is the reflectivity. It's basically the reflectivity. So With one single laser, we have two different signals that we can analyze. And this signal behaves differently when a particle passes through the channel. When the particle passes through the channel, the resonance frequency changes because of the mass, but also the reflectivity changes because of the scattering of light. This is a real measurement at real time, in which we can see a lot of different particles passing through the resonator in seconds, right? Each single event takes about 1 millisecond, approximately at these working pressures, and each of them is a single particle. So we have two different signals. Okay, that's why we can make measurements on the reflectivity. And the reflectivity we can simulate the scattering light, by the particle inside the microchannels. This is a real image captured by our CCD camera of the system, and we can see how the light is scattered by the light. So we have two minima because of the interaction of the one edge of the particle and the other. Okay, when it passes through the channel. So we have two different signals at the same time. If you remember this distribution at the beginning of PMMA particles and silica particles, which were very different in size and mass, the Boyan mass was exactly the same, basically. However, if we use optics instead of mechanics, we can distinguish them. This is the silica signal and the PMMA signal. So we have a double parameter detection, which allows discerning in between particles of similar Boyan masses but different materials. So therefore, the optics is mostly sensitive to the material, the mass is mostly sensitive to the density or the size, more or less. It's just to have a thumb rule. So let's make more and more measurements, right? Here we have the mechanical signal and the optical signal for silica particles. In this case, the mechanical signal changes because of the size of the particles. However, they were the same material. So the refractive index, this material is exactly the same, basically. Therefore, the optical signal is not enough to discern between them. However, when we have two different materials, the mechanical signal is barely discernible. So yeah, so we cannot make measurements or discern between these particles just by using mechanics. However, the optical signal is very different because of the refractive index. Then we can combine them in 2D plots or 2D maps, in which we have different particles depending on the reflectivity and the frequency shift of our device. It allows unambiguous discerning by combining optics and mechanics. Let's apply this for label-free cell discerning. In this case, we were using healthy and tumoral cells of the same mammalian tissue. They have the same size and a very similar density. So they were virtually identical cells, basically. So let's try it with our device. We have different known cells at the beginning, right? And we can obtain different points here corresponding to single cells in our maps. And we end up with a measurement in which we have the Boyan mass, the mass of the cells, which is mostly similar, or is exactly similar because they were from the same tissue. However, optically, they can be resolved because of the internal structure of the cell. This is what we see here, in which we have the frequency shift of one single cell, and it's not good enough just to understand it. However, optically we can do it. Okay, so the optical signal in this case allows discerning what mechanical signal may be used just to track biophysical parameters. So let's continue with these biophysical parameters. And now we have the size, okay? How can we measure the size? One thing that we can do is to measure the time it takes for a particle just to travel all around the suspended capillary, because we remember that we are using a locking amplifier. With this locking amplifier, we can lock to a frequency, which is the resonant frequency of the capillary, and make measurement or track this frequency as a function of time. And if we increase the pressure difference in between the ends of the channel, we can see how the particle goes faster and faster and faster as long as the differential pressure increases. Okay. This is what we call transit time. And this velocity is just calculated by, it's very simple, just the resonator length divided by this transit time, which is the time that the particle takes to travel all around the resonator. But we also have the optical signal, because this is not enough to calculate the size of this particle, just for the velocity. However, with the optical signal, we have this double peak that I mentioned before, because of the scattering light. We can distinguish 3 different regimes, 1, 2, and 3, and the time distance or the time difference in between these 2 points here give us this small differential time, which can be used to calculate the length, just multiplying by the velocity that it is that was calculated by using the mechanics. Okay, so we use the optical signal to calculate this travel time here, and the mechanical signal to calculate the velocity of the particle. By using this, we can make a lot of different measurements of different particles. In this case, where silica and in this case, where silica and PMMA, and we can see how good are our measurements when compared with a SEM analysis. I have to mention that, of course, we have more dispersion, but each single measurement of these particles just take 1 millisecond. The whole bunch of measurements here took like few minutes, let's say 2-3 minutes, in order to have hundreds or even thousands of measurements. However, in this case, the SEM analysis took like hours. So there's a trade-off between the time and the dispersion of the results, but the nominal values are similar. We can also confirm this velocity calculation just by increasing the flow rate over different values, just by including a differential pressure in our system, in our microchannel resonators. And we can see how 2 different particle populations disperse as a function of the pressure in the channels. Okay, and with these 3 different parameters, we can make our maps, in this case by adding a 3rd dimension here, which is the velocity. Actually, we have 3 different parameters measured by 3 different measurable signals, which were the frequency shift of the resonator, the reflectivity, and the velocity. That can be translated into mass, refractive index, and size, which are parameters, biophysical parameters, or our analytes. Let's think about how to measure the compressibility of these particles, cells, or wherever. We know that the particles flowing through the microchannel, which are those here. So this is a frame captured by our CCD camera in the system. They have, okay, if we think on this particle inside the channel, And if we make an analysis of the forces that are experiencing these particles, at the steady state, the summatory of this driving force and the dragging force, this dragging force is just the viscosity, right? Is mostly due to the viscosity, and this driving force is mostly due to the differential pressure in the channel. In the steady state, the summatory of these forces should be 0. Okay. However, there is another force in the vertical direction, which is the lifting force or the lift force. This lift force can be calculated just by this, okay, by this formula. And this force is transmitted to the resonator wall. If we have a force that is transmitted to the resonator wall, we are affecting also the dynamics of the system and also the frequency of the system, which can be calculated here. In this case, we have the hydrodynamic loading effect on the resonance frequency that can be calculated like this. This is the freestanding region and how this hydrodynamic loading affects the resonator dynamics on this just by flowing this particle inside the channel. And we can compare it with the mass effect, which is just the regular which follows the regular shapes that I showed you before. And here there's a question, is why we don't observe this kind of effects? This is because this mass effect is much larger than the hydrodynamic load. And why is that? Why we have this mass effect is much higher? This is because the stiffness contrast. As I told you, this is no more than a spring, a mass with a spring, and we have to take into account the spring constant of this system. In this case, we have the stiffness of the material itself, the stiffness of the resonator, which is the spring constant. We can make an analysis of the mass effect over the hydrodynamic loading for different materials or different stiffness of the system with different Young's modulus, basically. If we use a regular silicon nitride material, which is is very commonly used in clean room, we have that we always measure only the mass of the particles. We can never measure this hydrodynamic loading. We can also use silica, which is the kind of material that I showed you before in our glass capillaries. Silica is silicon dioxide, and we always measure only mass. However, if we make use of polymers, in this case SU8, which is a very hard polymer, it's a very stiff material, for a very large flow rates, let's say that maybe we can measure this effect. Okay, can try different polymers like PMMA or even PDMS. PDMS is a very soft material. I don't recommend to use it because for nanomechanical resonator, they provide a very hard and very terrible resonances with a very poor quality factors, but they're very soft. And in this case, the hydrodynamic loading is very large. Okay, PDMS is commonly used in microfluidics, so that's why we tried. Okay, so if we make the calculation of these polymer resonators made on PDMS, we have a force limit of detection of 1 piconewton, which should be enough to measuring the stiffness of cells. How we do that? Okay, so we have this hydrodynamic loading, which is basically a vertical force in this direction, pressing or pushing through the resonator wall. And then we have something which is soft like a cell. This particle deflects or deforms. Okay, a rigid particle doesn't affect the size of the particle. The hydrodynamic loading follows a straight line. However, if we make the calculation with cells, let's say a healthy cell or a tumoral cell, we have different behaviors. So in principle, this is the force and this is the Young's modulus of these cells. In principle, we can use it for discerning or to measure the compressibility of these cells or these soft materials. Okay, so let's try to make more analysis of different parameters. Just think about this. We are using only one laser, one photodetector, and all of those parameters are measured just by one single measurement. Okay, and just by treating the signal. That's what we do. So they can be used for measuring, for example, the density of the carrier liquid. We tried a long time ago to measure this resonance of the capillary filled with water or different mixtures of ethanol and glycerol. And we have different resonance frequency shift due to the mass density. So we can make measurements on the properties of the liquids. We can also measure the compressibility of these liquids. How can we do that? We include a second pump. Okay, so one pump is just to press on one side, and the particles flow from one side to the other. However, if we include two different pumps, and we put both pumps at the same time, and we turn it on, we can put a static pressure inside the channel, and this static pressure deforms the shape of the microchannel, changing the frequency shift. So we can measure the compressibility of different liquids just by measuring the slope of the resonance frequency as a function of the pressure. Okay, we can also measure the molecular mass of different gases, because well, following exactly the same principle that has been used in liquids, just by increasing the static pressure, we can measure the compressibility of gases which are related with the molecular mass. Okay, in this case, we have measurements, experimental measurements of carbon dioxide, air, oxygen, nitrogen, and helium, measuring their molecular masses. Great. So we have one single laser, one single photodetector, one or two pumps, and just one single measurement. We can measure different parameters. Okay, so we have a multi-parametric analysis. So in 2021, we incorporated Nanological, and we have the licensing of the patents 1 year later to apply this multi-parametric analysis, in this case for the identification of bacteria present in liquids, in this case blood sample. Why bacteria? Because of sepsis. Sepsis is an organ dysfunction which is caused by the dysregulated response of the body to an infection. Okay, when we have an infection and the bacteria reach the bloodstream, we enter in this sepsis state. Okay, this is the first cause of death in hospitals. This is the first cause of hospital readmission and the first cause of healthcare expenditure. It affects 50 million people worldwide, with 11 millions of global deaths per year. Okay, if you think about this, this is one death every 2.8 seconds. So 1/5 deaths worldwide is caused by sepsis. And this is a very problematic condition. It's not an illness, it's a condition, okay, because it's the dysregulated response of the body. This is a very complicated one because it's time dependent. Okay, so in this case, the time is crucial because the mortality rate increases 10% per hour once the shock septic is diagnosed. Okay, and the gold standard for identification of the bacteria that is causing this infection is the blood culture. The blood culture takes from 12 hours to 3 or 4 days to give a result. Okay, so this is too late. Basically, it's too late, because when the doctors, the medical doctors, know what are the bacteria that is causing this infection, to put the correct antibiotic, basically the patient is dead. So that's why these days the diagnosis is based on symptoms and secondary biomarkers. These secondary biomarkers are not specific. They only can say that you have something which is caused by an inflammatory effects, or is causing lactate axis in your blood system, but is not specific. So what people do these days is use a specific treatment, which is based on broad spectrum antibiotics by default. Okay, which is very expensive. It's very time consuming, because you never know if the treatment is correct or not. So you have to re-evaluate the treatment every 2 or 4 hours, and is contributing to the antibiotic resistance, which was identified by the United Nations as one of the most problematic or the most dangerous problems worldwide these days. So here is where Nanological is acting. Our solution, our value proposition, is based on 2 different things: the deep science and also the deep learning. Okay, deep science, because we are using these disposable microfluidic chips or cartridge measured by an optomechanical system that I showed you before. And we are using deep learning to analyze the data to improve the sensitivity and the specificity. Okay, we are also using Internet of Things, because we want to analyze this data on cloud and all servers to provide these artificial intelligence algorithms to improve the sensitivity and the accuracy of the diagnostics. We present Somia, which is our point of care product for this condition. We have results under 20 minutes from the blood extraction, from the blood analysis. So we don't need any kind of pre-treatment or marking the bacteria or growth. Okay, so just in 20 minutes we can have an analysis of an identification of this bacteria. How about it works? Okay, so we have our disposable microfluidic cartridge. I will show you pictures just later on. We put it onto our optomechanical measurement system, which is basically a laser. Here, in this case, is flip because the laser is vertical. Okay, so we have the laser here, and we have our locking amplifier. It's a digital one underneath. Okay, so we have the electronics right there. We collect the data and we analyze it by using our artificial intelligence algorithms. In this case, where there's a neural network. We analyze it, we obtain a result, and we provide the result to your computer. The microfluidics in this case is composed by this microfluidic cartridge. In this cartridge, we use a conventional vacuum tiner, which is this tubing for the blood. We put it onto the cartridge. We have a pre-selection or pre-separation of the blood to the plasma containing the bacteria. Here is all of this is made by microfluidics. There is no treatment, no chemical reagents or something. We have the optomechanical measurement, and we have our deep learning identification. In this case, we have E. coli, Klebsiella pneumoniae, and Staphylococcus aureus directly identified in blood plasma. Okay, and it took a few minutes. These are the results. We use a neural network, 7 layers of neural network, with a final layer of 3 different neurons. One of those for these three different bacteria families, E. coli, Klebsiella, and Staphylococcus aureus. We have an accuracy, which is the combination of the specificity, the sensitivity and the specificity of more than 96%. There's a note, whenever you have something which is better than 80% is considered good. We have 96% in blood plasma. This blood plasma was provided by the Centro de Transfusiones de la Comunidad de Madrid. I like to say that Nanological we're safe because it's composed by a very specific, very affordable. So the cost is not so high. We're also fast and very easy to use compared to the competitors. The business model is okay. So we are going to sell the device and also the consumables, and the market size is always growing because we always have this kind of conditions. And this is where we are right now. We are in this development and CE mark phase. I like to end the presentation just by showing a timeline here, okay? 10 years ago, we were working in the lab optical bench. This lab optical bench were free space, which means that we have a laser traveling through the air and it's collimated with an objective. More or less, the cost of the whole system with all the electronics and everything was about 200,000 euros. Then we incorporated Nanological, and from the beginning, we thought that the best way to do this is to use a fiber coupled system. Why fiber? Is because we don't want to have something which can be misaligned at the laboratory, at the clinical laboratory, because we want to be very easy to use for non-trained people. We have an MVP, working MVP, with enhanced noise dispersion. Is a vertical configuration, which simplifies the use, and they have a very good repetitivity and is movable, which is very useful because we work with hospitals and we want to put this machine right now in the hospital. However, we are also working on this alpha prototype. This is a working mock-up or working system right now. It's a preliminary working system because at the end of this year, we are going to start the certification for this CE mark. Also, we have the microfluidics part. At the beginning, we were working with clean room-based fabrication. This clean room-based fabrication was very expensive, also time-consuming. Like 3-4 years ago, we tried to use a fiber splicer because this kind of capillary were basically a fiber, and a 3D printer for the frames, the chips, the disposable chips. But now we are using two-photon polymerization. This two-photon polymerization machine is a 3D printer, but with a very, very high resolution. The resolution is about 150 nanometers, which is very good, and also is they allow us to use it as for mass production. Okay, this is the team right now, but we are hiring people. We were 4 founders, Blanca Caballero, which is the CEO, myself, and also we have founders here helping with the finance and the regulatory advisors. We have most of the team members are engineering. We have nanotechnology engineering, software engineering, product engineering, product development engineering, microfluidics, and also biomedical applications. And we have clinical collaborators, the Hospital Ramón y Cajal and the Hospital Universitario La Paz. So thank you very much for your attention. So, for questions.
Okay, so I don't know if someone of the audience has any question. You can switch on your microphone and maybe you can. Okay, if you want some time to think about them, I have a few, Maria, just some curiosities. I work on the biological applications, so they are more, I don't know, there is a comment, Marta, I don't know. Yeah, okay, then we can, okay. The first one, when you are talking about the diameter, the stiffness, because usually I work on the encapsulation of different therapies on liposomes or even exosomes, extracellular vesicles.
Yeah.
It could be possible to, for instance, differentiate this hydrodynamic size or stiffness when we put a nanotherapy, a nanoparticle inside our vectors, or
Depends on the size, right?
Okay.
Because right now we are limited by the wavelength. The
Okay.
laser that we are using, we're using a 633
Okay.
nanometer, which is basically a red laser.
Yeah.
And the minimum size that we can measure is about 800 millimeters.
Yeah, but more or
Which
less
is-
they are around 100, 200. So
100 to 100 nanometers.
yeah.
Okay, so maybe we're in the limit.
Okay.
Right? So below 500 nanometers, I think that we will have some problems. And
Okay.
we have to use a different
Okay.
wavelength, right?
Okay.
But it's just because of the wavelength of the
laser that
yes,
you are.
yes.
Okay. Marta? No hay? Okay. I have another curiosity.
Yeah.
In insomnia, when you said that you were able to differentiate among the different pathogens,
Yes.
maybe it's a non-logical question, but you have like to previously calibrate
Yes.
your
absolutely.
system with a lot of pathogens.
absolutely.
Okay.
Yeah. So the thing is, we have to fill a catalog of
Okay.
different particles. I'm sorry, particles of different pathogens.
Uh-huh.
And the way we do that is to go to the hospital, basically,
Okay.
and they give us different bacteria,
Okay.
right? Yeah, right. And we make a lot of different measurements in different conditions, different pressures, different temperatures, different
Okay.
environments and carbon liquids and everything. And we fill a complete catalog of these bacteria.
Okay.
And we train our neural network system
Okay.
just to show or to teach how to identify this.
And now just two curiosities about because I'm most on the basic research field, and as we are on Thursday NanoSpin-off talks of Cátedra Sanka, which are the most difficult things or challenges that you have found with patenting your system?
Not with the patents, because at the CSIC we have, we're very lucky because we have an office which is mostly dedicated on this. So
Okay.
they're very helpful at that time. Probably the most difficult part to incorporate a company or to start a spin-off company is to try to convince people, particularly the venture capitals,
That your instrument is
something which is going to be sold.
is worth to you.
Yes,
Okay. And then talking, because I understand now you have your system that we have seen how you start from the lab design to the clinical application. I think that then from a clinic, for instance, in a hospital, it's something very easy, and this is very important if you want to move to the clinic, that you don't need anyone with an special expertise to manipulate your system, right?
Exactly. So the good part of this design, and that's why we have a lot of engineers in the company, is to design this cartridge in which we use sabacutiner from conventional blood analysis, just to put it into the cartridge, and then the machine
goes everything, and you just read
exactly
the results. So
exactly. So it's autofocus is
okay. And just the last, I promise. Are you exploring some other different application, not only focus on pathogen detection? Maybe, I don't know, cancer, biomarker, I don't know.
That's
Okay.
Yeah, we're on that track.
Okay, so congratulations for the great talk. Thank you very much.
Thank you.
And it has been a pleasure discussing with you.
Thank you so much.